Welcome everyone to a series of electrical engineering videos that will go over the fundamentals of electrical circuits. Today we're going to talk about electric charge. Charge is an electrical property of the atomic particles of which matter consists of, and this is measured in coulombs, as we can see here. One moment, let me get the pen tool up, as we can see here. And usually electric charge in terms of symbols is represented as the letter Q. As we know from probably hopefully high school or university physics, that atoms are the building blocks of all matter, and they themselves are built from electrons, protons and neutrons. Experimentally, we know that the single charge of an electron is simply negative 1.602 times 10 to the negative 19 coulombs. From this information, we can then determine what the unit of a coulomb is, which is 1 over 1.602 times 10 to the negative 19, and what we get is 6.24 times 10 to the 18 electrons, which is a very large number. So during labs and experiments, we'll probably be only working with nano, micro, or pico coulombs. Moving on, we're going to briefly talk about the conservation of charge, which simply states that charges cannot be made or destroyed, only transferred. Knowing these things, we can now consider the flow of charge. A unique feature of electric charge is that it is mobile. That is, it can be moved from one place to another, where it can be converted into other forms of energy. Mathematically, we represent current as I, which is the rate of change of charge over time. So this, as we can see, is the change in charge over the change in time. So what this symbol means is delta, which simply means the change in, and this symbol, when you see it later on, simply means by definition. Okay, so what's interesting about this formula or mathematical way of portraying the flow of charge is that we can move things around. So for example, we can find the amount of charge on something if we know the current and the amount of time that object is exposed to that current. So I dt can be equal to dq simply by moving the dt across. So if you multiply both sides by dt, we get I dt over dq. In a battery attached to a conducting wire, what a battery is a direct current source, which we'll talk about in a second. And this is essentially a source of EMF. When we attach this to a conducting wires, the positive charges will move in one direction and the negative charges will move in a different direction, in the other direction. So what we have here, we can have something like this, right? This is essentially a cell, right? And then just think of cells as batteries, as just a source of power, source of energy, which allows currents to flow, or a source of EMF which allows current to flow. So what happens here is, this is the battery, the larger plate represents the positive end, and the smaller plate represents the negative end. And if we zoom in to the wire, we will see that there's negative and positive charges. Alright, so the positive charges, when attached, the charge is actually in the wire itself, and since now there's an EMF or electromotive force being applied to the wire, the charges will move. So the positive charges will be attracted to the negative end, so the positive charges will go to the negative end, and negative charges will go to the positive end. And what happens here is that there'll be a current, and it is conventional to take the movement of positive charges as the current flow, since I believe this was done by Benjamin Franklin, which was a famous scientist and inventor. You can find more information if you want about him. Just Wikipedia, Google something. Some pretty cool information out there. So yeah, he defined the movement of positive charges as a current flow, and ever since we've used that as convention, even though now we know that is actually the negative particles that causes currents. So moving on, we're going to talk about AC and DC currents. So what DC simply means is the current does not change with respect to time, which implies that the current is constant. This is represented usually with a big I, so like so. When we see this, we know it's a DC current. If we want to represent this as a graph, let's say the current provided is 1 amp. That means it's always constant at 1 amp, unless the source is switched off or something. So it remains constant. And AC current or alternating current, as you can guess, is a time-varying current, which is by convention represented with a small I. As you can see, it is a sinusoidally varying current, and what we represent this with is a small I, which means it changes with time. So, like so. And that is essentially all we need to know about current. So we're just going to do a few questions now, just to assist in our understanding of what current is. Okay, well, current and charge. So the first question is, how much charge is in 3,600 electrons? So based from the experimentally measured value of a single charge of an electron, right? We know that a single electron is the charge of it is negative 1.602 times 10 to the power of negative 19 C. So if we have 3,600 of these, we need to multiply this by 3,600. And the answer that we get typing this into the calculator is just give me a moment, is negative, this is pretty important since it's talking about electron here, negative 5.767 67 times 10 to the negative 16 C. And note here that we're given 4 sig figs for the value, and we should have 4 sig figs here. It's just a physics thing. Electrical engineering is less important, but it's still good. It's a good practice to maintain things like this. Okay, so the next question that we have is, a lightning bolt with 8 kiloamps strikes an object for 15 microseconds. How much charge is deposited on the object? So we know that kilo means 1,000, right? So what we're given is the current, which is I, the time, which is dt. So the unknown here, if we look at this equation that we can use, is the amount of charge, which is the change in charge, since we know the change in time and the current. So this relationship we found before, or we were given before, which was defined mathematically by definition, which was this, right? We can make this into dq if we multiply dt with both sides, equals I dt. And since we know what's the current and the change in time is, we can simply substitute these values in. Times 15 microseconds. Micro simply means 10 to the negative 6. Sometimes the question might write something like this, might write mu as seconds. That's just the common way that they'll do it sometimes, but they really just mean the same thing. And what we get in the end is 8 power of 3 times 15 to the power of -6. We get 0.12 amps. I hope you guys learnt a thing or two in this video, and I'll hopefully see you guys in the next video.